the magnetic flux, right?
Yes.
So, yeah, so there is a property associated with the magnetic flux. So, can you guys tell me uh, what did you learn about the electrostatic or electric flux? So, what was the electric flux in a closed surface? Do you guys remember? So before we start this Faraday's experiment, let me talk about the some resemblance with the electric flux. So can you guys tell me about what was the electric flux in closed surface?
It
Do you
was
guys?
zero.
Yeah. What did you say, Aisha?
Zero.
Electric flux inside a closed surface. Hmm. Or let me modify the question differently. What was the Gauss law for electric fields? Gauss law for electric flux. Q by epsilon zero. Yes, good. So okay, good. So we studied that. Yeah. So we studied that we had. Let's say we have this. We have this closed surface, right? And we calculated the electric flux in this closed surface, right? And this was from Gauss law, this was equal to Q enclosed by epsilon naught. So this was a Gauss law of electric field, right? Now, from this law, we understood about that what are the charges, right? So, but in the case of magnetic flux, so this is Gauss law for magnetic flux, right? And it says that if we calculate magnetic flux inside a closed loop, right? So this would give us okay. So there is a very important thing about this law, right? So you can get a Nobel Prize if you found something new about this law. So this law says that whatever, so let's say you have this magnet, right? And it has some electric flux. Let's say you are calculating this one, and then this one, and then let's say you are calculating this one and this one, and let's say this one and this one. So let's say we take a sphere. This is sphere. If we take this sphere and we calculate the number of electric field lines passing through this closed sphere, so how much would that be? So always remember that outgoing is 1, incoming is -1. So you have 1, 2, right? So you have 2 outgoing and then 2 incoming. So no, not 2, but 1, 2, 3, 4. 4 outgoing and then 4 incoming. So how much is that? Right. So whatever the number of electric field lines in a magnet goes outward in a closed surface, it always comes back. Right. So this law states that magnets exist in dipoles. So magnet doesn't have magnetic monopoles. So if you guys can discover the magnetic monopole, then you guys will get Nobel Prize. If you can discover the magnetic monopoles. So have you seen a magnet which has only north pole,
No, sir.
right? So the magnets always comes in dipole. So we can never, if we cut this magnet, right? So if we have this magnet, so this is north and south, and if we cut this magnet in half, so this will become south and this will become north, right? So this is the property of the magnets, that it will always come in pairs, right? It will always have dipoles. But for the case of charge, right? For the case of charge, let's say if we have a positive charge, so you guys have already learned that this will have always outgoing lines. So if we calculate the electric flux, so this would be how much? 1, 2, 3, 4, 5, 6, 7, 3, 3, 4, 7, and 8. So you can see that this tells us that in a closed loop we have some charges. So this tells us about that electric charges can have monopoles, but magnetic magnets can't have right. Whatever the amount of magnetic field line will go out, so it will always come back. Is this point clear?
Yes, sir.
Yes.
So this is what we call the Gauss law of magnetic flux. Okay, you guys please note it down, and then we'll do the next one. Please note it down. And if you guys have any doubt, so please ask. This law tells about the magnetic monopoles. Okay.
Got it.
Done. Okay, note this one. This is a charge, right? Done, everyone. Yes, Mariam and Aisha.
Yes, sir.
Okay, so now let us quickly talk about Faraday's experiment. So this experiment tells us that changing magnetic flux will create EMF or voltage, right? So this is the Faraday's experiment, and there are three cases so he experimented this case in three ways. So there are three cases, right? So first case is that we have. So let's say first condition is that we have this coil, and we have connected this coil to some galvanoid, right? It has some. So this is some galvanoid. and we have connected this circuit. So will you get any deflection through this circuit? Yeah, you have a coil, and then it is, and then you just connected this coil with some galvanometer. So will you get any deflection, guys?
No, sir.
Yes.
No, sir.
So are you saying no, Maria?
Yes, sir.
Yeah, because we don't have any current. So how will this galvanometer will deflect, right? It will show any deflection. So now what happens is that what Faraday did or what Henry did, that he so he placed some magnet, right? Let's say this is north and this is south. So let's say that this magnet was here. So some electric field lines is crossing through this, right? So some electric field lines are crossing through this coil. Okay. So okay. Now this is fixed. So there is a fixed electric flux through this coil, right? Some magnetic field lines are crossing through these coils. Understood?
Yes, sir.
So we know that in a magnet, we know that this is north and this is south pole. So in close vicinity, we have a large number of magnetic field lines. So which shows that in close vicinity, the magnetic field strength is high, right? So if we move this bar magnet closer to this, so let's say we are moving this bar magnet in this side. So now it has reached here. Okay. So then it will. So then what will happen? Flux will remain same or flux will increase?
It will increase.
Flux will increase, right? So flux is changing. Similarly, what you do is that you move this bar magnet away from this coil, right? So what will happen? Flux will decrease or increase.
Decrease.
So you see that in both the cases, flux is changing through this coil, right? So in the first case, let's say that in the first case, the galvanometer shows a deflection in this side, right? But when you move this coil away from this, so when you move this magnet away from this coil, so then it will show a deflection in opposite direction. So then the current would be in the opposite direction. Is this experiment clear to you, everyone?
Yes, sir.
Okay, so
You
this
can
was,
just say,
yeah, this was the first experiment. So this was case one. Okay. Now in the second case, what Henry or what Faraday did was that in place of, so in place of a magnet, he uh, placed some another coil, right? So this is like a solid one. He placed some another coil and applied some voltage in that coil. So which means that some current is passing through this coil. Then it will create, similar to that bar magnet, it will create some magnetic field, right? So it will have some magnetic. Now what you do is that now you move this coil. You move away or you move away this coil or you move closer to this coil. So then again, what will happen?
And increase or decrease in the flux.
Absolutely right. Then again it will show some deflection. Then again it will show some deflection in both the sides. Is this part clear?
Yes,
Okay, so who has yeah. Can you explain again? Oh, which part? Which part, Aisha? This part.
Yes.
So this part you are saying.
Yes, sir.
You are saying no. So which part do you want me to explain?
Sir, the first one only.
First one only. Okay. So yeah. So this is a magnet, right? This is a magnet and it has some magnetic field line. And we know that closer to this north pole, the magnetic strength is larger. There is a larger number of magnetic field lines crossing through this area in spite of or in place of this one. So in this region, you will have some less number of magnetic field. Let's say in here you have two, but in here you will have how many? Six, right? So when you move this magnet closer to this coil, then you are changing the magnetic flux through this region, right? And this Faraday experiment showed that whenever we change magnetic flux, then it will create EMF, which will, so some voltage will flow, and then due to that voltage, some current will be produced. Is this part clear?
Yes, sir.
Okay, so that is what I was saying. And when you move away this magnet, then also the magnetic flux will decrease through this coil, and then again the EMF will be produced, but in the opposite direction current. Clear?
Yes, sir.
Yes, is this clear, Aisha?
Yes, sir.
Okay, so now the similar case, but in the case of bar magnet, you replace the bar magnet with some another coil, which has some current flowing through this. So you already know that for solenoid, you have this magnetic field which will go in the. So this will behave like a bar magnet, right? So in similar case, when you move this coil closer to this coil, then EMF will produce, right? And when you move away this coil again, then flux will change so that your EMF will produce. So this galvanometer will show a deflection, right? So that is what I was talking about. Is this clear, Aisha?
Yes, sir.
Okay, so now the third case is that where did my okay, so did I yeah, so let us join and then start. Yes, Mariam, you got disconnected. So we are
yes,
talking about we are talking about the third case. So we have coil and we have this galvanometer, right? And what we do is that we have another coil, and then what we do is that we have this switch, right? And then this is okay. So what we do is that as soon as we connect this switch, so as soon as we connect this switch, so momentarily the current will start increasing, right? As soon as we just switch on this device, switch on this circuit, right? As soon as we connect this circuit, then momentarily the current will increase, and at some point later the current would be fixed, right? So we are not moving both the coils. In this case, we are not moving both the coils, but both are stationary. But we are just switching on and switching off this device. So what happens is that as soon as you just switch on this device, switch on this circuit, then momentarily this galvanometer will show deflection. But after a very few seconds, after very hundredth of second, the current would be become constant in this circuit, and then this deflection would be again zero because no flux is changed. So, but momentarily, when the current was flowing through this circuit, right? The current started to flow this in the circuit, then some flux changed in this device, and then it produced some EMF, right? So these are the three cases. Is the third one case third case clear to you guys? So in the third case, we are not moving the coil. We are just switching on or switching off the coil, right? So just switching on, then the current will start to increase. It will have some current momentarily, and then it will become constant just after a few seconds. But between that time, the current was changing in this coil. So this coil will have different kinds of magnetic field. Then the magnetic flux through this region will change. So it momentarily will produce an EMF, right? And then after some time it will become, when the current become constant, which means that the magnetic field across this coil has become constant, then there are same number of magnetic field lines passing through this region, which means that the galvanometer will show a zero deflection because your flux is not changing, right? Is the third case clear to you guys? Yes, Aisha and Mari. Yes.
Yes, sir.
You are saying yes or no?
Yes, sir.
Oh, yes. Okay. So good. So, what did we understand in these three experiments? What did we understand? What did we understand, guys? In the experiment, in the following experiment, what did we understand?
Now, when the magnetic flux is changed, it will create a deflection in the galvanometer.
Yeah, absolutely right. So whenever we change the magnetic flux, then it will induce some voltage in the circuit. So that is the crux of that Faraday's experiment. In all the three cases, we saw that whenever we change magnetic flux inside the coil, then it will change or then it will create some EMF. It will create some voltage, induced voltage. Okay, so now let us talk about Faraday's law. So Faraday's law, right? But you guys first note down this part, right? I didn't write so much thing, but I just explain these three. So you guys just note it down. Okay, these are three cases. And if you guys have any doubts, so please ask. So in two cases, we are moving the coil, right? Moving the magnet or moving the coil. But in the third case, we are just switching on or switching off. Yes. Should I scroll down, guys?
It's one.
So this is moving, right? Or moving. This will show some difference. And whenever you guys have noted it down, step.
So,
Done. Okay, so now we already what is a Faraday. So it says that rate of change of magnetic flux is proportional to induced voltage. Okay. So let's say you have a phi 1 initial magnetic flux, and then you have phi 2 final magnetic flux. So change is called delta phi, right? So this is change in flux. This is what? Phi 2 minus phi. And then you have change in time also. This is, let's say, T2 minus T1, which is initial minus final time, right? So this law says that, Faraday law says that the induced EMF will be equal to minus of delta phi by delta. This is proportional. Okay. So when you remove this proportionality, you will get, or let me write. So this is proportional. So when you remove this proportionality, you will get K, and then this K experimentally is found to be minus. So why this minus comes, you guys will know about it in Lenz law, right? So when we study the Lenz law, which talks about the conservation of energy, so then we'll be able to know that why this minus comes, right? Is this part clear, guys?
yes,
Okay, so what is this? What is this delta phi by delta t? Yeah,
using constant change in time.
yeah. So when we write a delta, so this gives us average, right?
Yes,
So E average is minus delta phi by delta t. So similarly, if I want to calculate E instantaneous, right? So this would be how much? Minus t phi by dt. Is this part clear, guys? Is this part clear?
yes,
Okay. And we want to, so this is our EMF, right? So E is minus t phi by d. Okay. So we know that current is how much? Current is V by R, right? So this is V by R. So this would be minus 1 by R d phi by d. So current, or let me write it as small r. This is induced current. Okay. So induced current is minus 1 by R d phi by d. This is induced EMF. Or induced voltage, and this is induced current. And if we want to calculate the charge, which is induced, so this would be equal to, we know that I is what? What is I in terms of instantaneous current? In terms of charge, what is that? Yes, what is current? Third chapter. What is current, guys? What is electric current? Yeah, some of you is talking, but I cannot. Yes, Aisha and Mariam, what is current? Electric current.
It's the flow of charge.
Rate of flow of charge, right? So this is dq by dt. Right, guys?
Yes,
This, this is equal to minus 1 over r d phi by dt. So then this dq by dt is minus 1 over r d phi by dt. dt cancels, and we have dq, which is minus d phi minus d phi by r. Okay, so if we write it in average terms, so this is delta q, this is minus of delta phi by. So these are this is induced charge. Okay, any problem in these guys?
no,
Okay, so please note it down, and then we do some numericals based on. And from tomorrow, you'll have some revision test, guys. Right? So on 1st September, and then on 8th September, and on 15th September, we'll have a revision test. So on 1st September, we'll have first two chapter, then next two, and then next. These would be the syllabus, guys. Okay.
yes,
Please prepare well, and right. So okay, whenever you guys want me to scroll down the screen, guys, It's whenever you guys want me to scroll down the screen, guys, please tell me.
You can scroll.
Noted. So then note, please note this point. Yeah, so whenever you guys have noted it down, please tell.
Answer.
Noted. Yes. Mariam and Aisha noted, guys.
Yes.
Okay. So now let us do some question and then we'll understand about length. So the flux and area is varying by let's say 40 squared plus squared 5. So find, and this is magnetic flux, so that is right, that is Weber. Okay. So find the EMF generated from let's say 0 to 2 seconds. And second question is that find the EMF induced at t equal to 4 seconds. So these are the two questions. Oh, Mayam got disconnected. So did you understand the problem, Aisha?
Yes.
Yeah, we have this flux which is varying like, and then you have to calculate, right? So this is in Weber, and then you have to calculate what is this EMF. So we are calculating the EMF in a span of time. So then what EMF we should calculate in this case? We have two kinds of EMF, average and instantaneous. So what EMF we should calculate in the first case? Yes,
Average.
average, right?
Yes.
Okay, okay. So yeah, one moment. Yeah, you calculate and tell me and give me one. Yes. Okay, so this is the question that we are calculating, Maya. Please calculate and tell me the answer. Yes. What did you guys get, guys?
1 minute, sir.
Yes, Maya, are you calculating also? Okay, so we have so in a coil, right? We have a coil in which in the coil the flux is varying like this, right? In that coil the flux is varying like this, and we have to calculate the EMF induced from 0 to 2 seconds, right? And then we have to find out that EMF induced at t equal to 4 seconds. So we have this first case and this is the second. So in these two situations, we have to calculate the EMF induced. Understood the question, Maria?
Yes, sir.
Yeah, please calculate, guys, and tell me quickly. I'll have to complete at least length off. So today I want to complete the length off.
I sent it in the chat.
Yeah, what did you get? Yes, Aisha. Oh, you have sent the answer. Okay, so you got 31 by 2 for the first. So let us understand, right? So what do we know? We know that phi initial. In the first case, we have to calculate the EMF. So we have to calculate the EMF in this time span, which means that we have to calculate the average EMF, right? So average EMF is what? Minus delta phi by delta t. And in the second case, we are calculating the EMF at an instant. So in this case, we have to calculate instantaneous EMF, which is minus d phi by d. Okay, so these are the two things. Now let us calculate. So delta phi, meaning phi initial is how much? Let me say that phi initial is 4 into 0 square plus 3 into 0 plus 5. So this is phi. And what is phi final? So this is 2. So 4 into 2 square plus 3 into 2 plus 5. So this is 16 plus 6 plus 5. So this is how much? This is 11 and then 16, so 27, right? And then we have this EMF average, which would be what? Minus of phi 2 minus phi 1 divided by T2 minus T1. This is minus of 27 minus 5, and then this is 2 minus 3. This is minus 22 by 2, which is minus 11. So minus 11 volt. How did you get Aisha 31?
And Q and the 5. IL, I did it 3 into
Oh,
5.
oh, you applied Q. Oh, sorry. So this was square, right? Yes, Mariam, did you understand this part?
Yes, sir.
Now the second is instantaneous one. So we have to calculate instantaneous one. That is minus d phi by dt. This is minus of d by dt of phi is what? 4t squared plus 3t plus 5. So this would be, is this the one? 4t squared plus 3t. So then this would be how much? This would be 8t minus and plus 3. And what is the value of t? So this is 8 into 4 plus 3. So this is minus 35 volts. So this is EMF. Is this part clear, guys?
Yes.
Okay, you guys, please note down. You guys have already noted down the question. So please, did you guys note down the question?
Yes.
If you, okay, so then please note down this question part and quickly note it down. Then we'll understand about the lens law. We will do one question, which is from the NCIT, and then we will do the lens law.
Sir, can you please scroll down?
Yes. Whenever you guys have noted it down, please check. Yes, noted everyone?
So,
Noted. Mariam, what about you?
Yes, sir, done.
So now let us do one problem more, which is of NCIT, and then we'll do. So let's say that a coil of an area is placed perpendicular to the magnetic field. A coil of an area A, okay, is placed perpendicular to the magnetic field B, right? And then it rotates at an equal rate and complete one revolution in, or complete one rotation. Complete one rotation in time t. Okay. So now we have to find EMF induced from 0 to 90 degrees. And second question is that we have to find out EMF induced from 0 to 180. Right. Complete rotation is how much degree? Yes. Complete rotation is how much degree? Yes, Maria, what are you saying?
Got it.
Complete rotation is? Yeah, what are you saying, Maria? So complete rotation is that when you move this thing and do a complete rotation. So which means that you have completed 360-degree angle, right? 360-degree angle. This is complete rotation. Yes, yes, you are correct. So now what is happening is that, so you have, so you have an area of coil. So this is a coil of an area A, and the magnetic field is perpendicular to this area. Okay. So what is the angle between area vector and magnetic field? What is the angle?
90,
Yes, Aisha, what did you say?
90.
Yes, 90. Okay, so Aisha is saying 90. Remember the angle or the angle of area vector. So what is, remember the direction of the area vector. That is what I want to point out. So yes, Mariam, what is your answer? Aisha is saying 90 degrees. Now Aisha is saying 60 degrees. So it is placed perpendicular. Okay, so Aisha is saying 60-degree. Mariam, what is your answer? Mariam is also agreeing to 60. Okay, without knowing the magnetic field. This is our coil in the YZ plane. In the YZ plane, this is our coil. Now, what is the normal to this plane? What
Area
is the normal to this? Yes,
vector.
Yeah, so area direction of the area vector would be normal to this plane, right? So this is the normal to the plane, right?
Yes, sir.
Yes, sir.
This is a surface, and then this is the normal to this plane. So this is the direction of the area, right?
Yes,
Right,
sir.
guys? And magnetic field is also going in this direction. So what is the angle between magnetic field and the area vector?
0.
Mm,
Zero. So now, okay, so it is zero. Now, let me, okay, so that is zero. Understood. Now, what I do is that I have this coil. Now I rotate it by 90 degrees. So this is my 90 degree, right? So I have this coil and then I have rotated it by 90 degrees, right? So now can you tell me what would be my area vector direction? So area vector, let me say it like this. So I have, so this is my area vector, right? Now I rotate it with 90 degrees. In my direction I am rotating. So now the area vector is this one, right? Area vector is this one, and what is my magnetic field? Magnetic field is this one. So now what is the angle between magnetic field and area vector?
90.
90 degrees. So if I rotate it by 90 degree, then the angle between this one and this one is 90, right? Now if I do one revolution, okay. So now what is the angle? So this was this. Now if I have rotated it in this way, complete uh, 180 or 180 degree rotation. So now what is the area vector? This one, right? This is the area vector, and this is the magnetic field. So what is the angle between magnetic field and
180.
180? Good. So now you guys have gotten the angle, right? So I had this one area, then I rotated it this, then I rotated it this, and then this is 180, and then 270, and then 360. So in 370, 360, it will have a complete rotation. But okay, so now you guys know all these. So first, from let us we have this. So we have this coil, right? We have this coil, and its area vector is this one. This is n hat, and the magnetic field is also in this direction, right? So in the first case, what is the flux? Let's say initial. What is the flux? That is B dot A, which is what? This is B A, and cos of what degree?
0.
0 degree. So this is B A, right? So this is B A. Now at 90 degrees, right? What is my B dot A? So what is my angle? What is my angle?
Cos 90.
0.
90. 0. I have rotated it by 90 degrees. So you saw that what was the angle.
Yes, sir.
So then, right, so then it is 90. So this is, oh, you are saying the total flux is 0. Good. So this would be the, right. Now, okay. Now when I rotate it by 180 degree, right. So now what is the angle between B and A? What is the angle?
180.
180, right? So this is minus of B. Okay, yeah. So if it is completing one rotation, meaning that, okay, so let me again. Okay, so this was this, and then I move 90, and then 180. So in 180, it is also completing one rotation, right? One complete rotation, right, guys?
Yes.
So in 180 itself, it is completing one rotation, right? One complete rotation. So let's say that that time is t, but you remember, this is not the exact same position. If I want to make it exact same position, then I'll have to rotate it by 360 degrees. So when I rotate by 360 degree, I will get the initial position. But when I rotate by 180 degree, then the position would be opposite, right? Okay, so now, so let's say that for 180 degree, let me change the equation that, right? So let's say that complete one rotation, right? This is time t. So complete one rotation is 180 degree. Okay, this is I'm saying one complete rotation. Now, what would be my EMF induced? So in first case, EMF induced in 90 degree. So that would be phi 2 minus of phi 90 minus phi initial divided by, and you see that, you guys see that we are rotating at equal rate. So let's say for complete rotation, it took t time. So for 90 rotation, what will be the time, guys?
90.
Yeah, so t by 2, right? Half time. Is that clear, guys? So this would be t half, right? So this is t by 2. So this is minus of, this was 0 and minus of VA. And then this is t into 2. So this minus minus cancels and we have 2 VA by t. This is the first case, right? Now when we rotate it to, let's say, 180 degree. So now this would be minus of phi 180 minus phi initial. This is in t time. So this is minus of, let's say, minus of VA, minus of VA. And then this is t. So this is again minus of 2 VA by t. So then again it cancel out, right? And then we'll again get 2 VA by t. So you see that equal amount of EMF is induced in both the rotation. Is this part clear, guys?
Yes.
Okay, you guys quickly note it down, and then we'll do the length down. And if you guys have any doubts, so please ask. And whenever you guys want me to scroll down the screen, guys, I can.
Ramsey.
Done. Then please note down. Yeah, whenever you guys have noted it down.
Ramsey.
Okay, Mariam, what about you? Did you complete?
One second, sir.
Okay. Yeah, please note it down and then we will do the length round.
Done, sir.
Yes. So the next topic is length round. Right. So what does it say? It says that the direction of the induced current will be in such a way that it will oppose the change in flux. So this is how the nature is, right? It always opposes the change, right? So it wants to be static, right? Stable. So the current in the circuit will be produced in such a direction that it will oppose the change in flux, right? So this is what the Lenz law is, right? And it happens or it shows the conservation of energy. Okay, so there are two ways to understand the Lenz law, right? There are two ways. So one way is that let's say you have, so we have, let's say you have a magnet, right? And this is north and this is south. And you have this coil, right? So let me remind you that if I have the current which is moving in this direction, so this will behave like south pole if the current is in this direction. And if the current is in this direction, so this will behave like, right. So this would be the north pole and this would be the south. Is this part clear, guys? Is this
Yes.
part clear? And we already know that north pole and north pole, they repel each other, right? And north pole and south pole, they attract each other, right? Okay. So the Lenz's law will tell you that in which direction the current will be. So let's say that you are moving this magnet in this direction, right? So you are moving the magnet in this direction, right? So this is coming in your way, approaching to this coil. So what will this coil will do? What this coil will do? This coil will try to oppose the motion of this magnet, right?
Yes.
So what polarity or what pole should be generated here so that it will repel this magnet? What pole should be generated?
South Pole.
Yes,
South Pole.
North pole, right? If it is North pole, then if it is North pole, so this would be in this way. So if it is North pole, then North and North will repel each other. So this would be the direction of the induced current. So that is how we tell the direction of the induced current. Is this part clear?
Yes.
Okay. And now you guys tell me that if I have this coil and I am, so this is my magnet. And what I am doing is that I am taking or moving away from this coil. So I am moving this magnet in this direction. So what should be the polarity of this coil? What should this coil do? It is moving away from the bar. It is away moving away from this coil. The magnet is moving away from the coil. So what should coil do to oppose the motion? It what should the coil do? It should attract or repel.
Repel.
Yes, yes, Aisha. Yeah, Mariam, what are you saying?
Repel.
Repel. So now you see that it is already moving away. So if it will repel, then it is going in the direction or it is not opposing. It is just enhancing the movement, right? So it is going in the direction of the motion. But we want to oppose this motion. So you guys tell me that it should attract or repel. This is going away. So what does it do? What should it do?
Should attract.
Attract, right? So if it is attracting, the what pole should be generated here?
South.
South. So this is south, right? So this is in this direction. Is this point clear to you guys? Yeah, is this clear?
Yes.
Okay, now let's say that you have, so now you have south. South, this is north, and you have this coil. And now I am moving this coil closer to this, moving this magnet closer to this coil. So what pole should be generated here? Hmm? Mariam is saying what?
North.
North. Your voice is very faint. What did you say? North or south?
North.
Can you hear, Aisha, did you hear what Mariam said?
No, sir.
Okay, let's say that you are saying north. Okay. North, okay, Mariam is saying north. Now, Aisha, what is your answer? This south pole is approaching. This is moving in the direction. So what should be the polarity of this coil so that it opposes the motion of this magnet?
South.
What should south?
Yes.
Okay, so now Mariam has changed the answer, so it is south. Good, good guys. So yeah, south would be the answer. Right. So this should be south. Yes. This is south. So this is where we reduce the direction from the Lenz's law. We reduce the direction of the induced current. So yeah, I will continue from here in the next class, and I will do the second case. But in the meanwhile, you guys will think about this question. So we have this north and south pole, and we have two coils. This is one, and this is second coil. The question is that the magnet is moving in this way. So what would be the polarity of this and this coil? This is the question. You guys think about it and tell me in the next class. But before that, you guys please note it down. So this was case first, and we will understand about the other scenario as well. So there is another way with which we can identify the direction of the induced current. Yes, first coil should be south. Oh, so you already okay. First coil should be south, right? So and what about this coil? South. Good. So this is also south. Good, good. So both would be south. Yes, yes. Ma'am. Yeah. So please note down this question, this part. And you guys have active class assessment test. So you also please, yeah, please take that test. And from
Done,
tomorrow,
sir.
done already. Okay. And from tomorrow, you guys will have some revision tests. So please take that. The syllabus is first two chapters. Let me again check the syllabus.
What answer?
Yes, noted, Maria.
Yes, sir. I was asking what time?
What time? So the Learnivio team will tell you about the time. I don't know the timing,
Oh,
so
this is
they will tell.
Test?
Yes, Mariam?
Is it like the fortnightly test?
Yeah, this is like a revision test, right? So, yeah, the chapters, all the chapters that you have studied so far, so on the basis of that, the test will happen. So, electric charges and field and electrostatic potential and capacitance. Yes, so this is the on week one, and then week two is current electricity, magnetic effect of current, and week three is magnetism and matters. Yes, these would be the syllabus. Okay, so noted everybody.
Yes, sir.
Okay, you guys, please log into Learnivio account and take the active test. And if you have activated the test, then you guys can leave, right? Okay, so Rifa has come. So yeah, you guys, please take that test. Allah Hafiz, guys, and but you guys, please take that test, complete that test. Okay. Allah Hafiz, Aisha, and Allah Hafiz, Maria.
Thank you.
Yeah, you guys, but take that test. Okay. Yes. Allah Hafiz, Aisha. Okay, so Assalamu alaikum, Arifa. Yes, can you hear me, Rifa?
Walaikum salam.
How are you, Rifa? All good.
Yeah, I'm good.